The speed of light is pretty famous. It shows up all over and has a finite speed of 3 × 10⁸ meters per second in a vacuum. But have you ever wondered how we figured out that the speed of light must be finite in the first place? Why can't it be infinite? The finite speed of light was proven by a Danish astronomer named Ole Rømer. When Rømer made his discovery in 1676, he was just 32 years old and was working at the Royal Observatory in Paris for Giovanni Domenico Cassini. Cassini was measuring the time intervals between eclipses of Jupiter's moon Io for the purpose of calculating longitude. He noticed discrepancies in his measurements but did not pursue the issue further. Rømer decided to look into it. Rømer saw that the time interval between eclipses was longer when Earth was moving away from Jupiter than when Earth was moving towards Jupiter. He concluded that this must be due to a finite speed of light. But how did he know this? Here's our solar system. Every time Io enters or exits Jupiter's shadow, light carries this information to Earth. Usually, you can either see the entry or the exit for a given eclipse, but not both. The other one is blocked by Jupiter. So you will either see periodic appearances of Io from Jupiter's shadow or periodic disappearances. We can think of these as signals emitted at a regular interval. Io's orbital period is about 42.5 hours. If the speed of light were infinite, the signals would arrive at Earth the moment they were emitted, so an observer on Earth would always see them 42.5 hours apart, regardless of which way Earth was moving. This doesn't explain Rømer's discrepancy. Let's think about what happens if we have a finite speed of light. Here's an analogy. If my brother and I are playing tag and I just stand still, it'll take some amount of time for him to catch me. If I run towards him, it'll take less time, and if I run away, it'll take more time. If light has a finite speed like my brother, the same effect occurs. If Earth were stationary, every signal would take the same amount of time to reach Earth, so an observer on Earth would still see the signals 42.5 hours apart. However, we know that Earth orbits around the Sun. When it's moving towards Jupiter, the observer sees the signals less than 42.5 hours apart, and when it's moving away from Jupiter, the observer sees the signals more than 42.5 hours apart. You can actually use the timing between eclipses to calculate a value for the speed of light, but today we have far more accurate methods. So why do we still care about Rømer's work? Well, the fact that light must have a finite speed is a critical aspect of modern physics and astronomy, and you can think about some of the implications yourself. Just go outside tonight, look up at the stars, and take a moment to appreciate that you are literally looking back in time. Thanks to Rømer, we know that signal left long ago and is just now reaching you, because everything, even light, has a speed limit.